So, I'm going to talk about when we have to fight against our own runtime. A few words about me. I'm a software engineer. I work for Red Hat, but I'm in the virtualization team. I'm learning my way in the container world, which is implemented in mostly, well, the tools are mostly implemented in Go, so here I am. How this talk is organized, we'll start our journey in the container world, like I did, and we'll find some hurdles in unexpected places, but we will see how to overcome them. Here there is my GitHub page on which you can find the slides, which I think will be also uploaded on the conference website. Let's start talking about containers. A refresh about how our container is. Our container is a Linux process, like Bash, like Firefox, like any other process, but it has few features. It uses a few features of the Linux kernel that allows us to contain the process itself to make sure it doesn't use more resources that we want to, and doesn't do unexpected things to our system. So we can safely run containers built by someone else on our own hosts without fear of breakage and stuff. Another key property is that using containers we can get a process, a program running as much as possible, or possibly exactly like the container author meant to be. So the reproducibility is one of key factors of container that when one wants us to use them. In order to run container, we need to use some tools, which are, well, they could be called the container engine, container runtimes, like I did in the slides, but essentially they are tools that allows us to execute those processes, to bring those images, those packages which we downloaded from a repository and create a container out of them. I'm quite sure everyone at least heard about Docker, which is one of those tools, the most popular probably, but there are others. Like, for example, Rocket, a couple of years ago, was tried to be a strong alternative. Recently, also CRI-O is another important alternative. And talking about container, we need to mention Kubernetes. So, because it's another name which pops up frequently. Kubernetes, however, is more a management platform, meaning that it actually needs a tool, a container runtime, to actually run the containers. Kubernetes concerns itself with the management of the containers on a fleet of hosts. So it's important, it's part of the ecosystem, but it's built on top of container engines. RunSea. RunSea is actually the very tool which every container runtime uses to do the work, the dirty work, to set up all the things we need to create a container. RunSea is a command line tool which was extracted from the Docker code base when a massive modularization happened around 2015. And it is pretty much the tool which every container engine uses, because, for example, Docker nowadays, it uses itself RunSea embedded, and also other tools ultimately use RunSea. It is not another requirement, it's just that most tools happen to use RunSea under the hood. Here is how RunSea fits in the picture. We have containerd, which is another tool which was extracted from the coder doc base, which is the management daemon, because we want to have a management daemon which helps us assess the health of a container, gets the health is running correctly, to get the metrics and so forth. So we need a supervisor. And RunSea fits in the picture. You can see it is embedded in the red box, because RunSea, it is actually used only to start the container. If you think that RunSea is for containers what a bootloader is for an operating system, is not an exact definition, but it is a pretty good approximation, meaning that RunSea sets up the environment, and when its job is done, it's no longer executing. So you don't see it running. You see it only when things are booting up. what RunSea does. So it uses some key features of the Linux kernel to build these scaffolding protection around the processes, to build those containment walls we mentioned previously. For example, it uses C groups to make sure that our process just uses a given quota of the system resources, and we can also do the accounting using C groups. It uses, it sets up a Linux and seccomp to make sure that our process is not doing some harmful. It just uses the minimum privileges it needs to run. And it also sets up the namespace, which is a key feature that defines the container in Linux. And it's exactly when dealing with namespace that we found an unexpected hurdle. Let's just review what a namespace is in this context. If you think again, the same thing, namespaces for a programming language and namespace in Linux, again, it's not a good definition, but it's good enough approximation to get a grasp of the concept. A namespace allows us to re-instantiate a global system resource in a local scope, making sure that our own container seeing a part of a system resources, making believe that it is a global resource, but it is actually just a fraction. We'll see. We expand this concept in a moment. To work with namespace, the Linux kernel gives us few tools in the form of syscalls, so function we need to call of the Linux kernel. Clone, which is the very same tool we use to create the processes, gets a new set of flags to make sure we can create a namespace like we want, if we want. setNS allows us to join an existing namespace. Keep that in mind. It is coming again in a moment. And also unshare for a already created process to join another namespace. Okay, let's set up the stage. Let's to have an example of this hurdle and what it means. Let's say we have a global namespace, global outer namespace, which is the system namespace, the namespace on which we boot. When the system boots, it has an implicit namespace, the global one. And let's pretend or assume we want to work with nested namespace, so let's have just one inner namespace. Let's also say that we want to do our work in a long-running program, meaning not a program that just do our stuff and exits. It's want to do that periodically maybe or just repeatedly. So this picture, it's an example of what I meant. We have the green box, which is actually the system process tree, and we have the red box, it is a tiny process subtree, and in the red box you can see, for example, the leftmost process believes to be the number one, and it is the number one in the container namespace, but not in the system, in the outer namespace. The processes are being remapped. You can apply the very same concept, for example, for the file system view. You can get a subtree and make believe that the root of that subtree is actually the root of the system for the process running in that namespace. There are more namespace than that, but it's enough to get the idea. So we want to jump in this inner namespace, and we can use this setNS system call to move ourselves into the new namespace. We start reading the manual page of the system called setNS, and we learn first that setNS reassociates a thread to a namespace. And let's keep in mind that the namespace is a property of a thread. So it seems easy enough. Let's comment this code snippet. We have a function which is going to run in a goroutine. Of course, even though if we don't explicitly ask the runtime to do that, we always run in a goroutine. So we remember that a namespace is a thread property, and we lock ourselves to a thread, meaning we ask the Go scheduler to make sure that this goroutine is always run on the same thread. We don't care which thread is it, but we want to run on the same thread. We will see again how threads get into play in a moment. But for now, let's just see that this goroutine is locked to a thread, pinned to a thread. So we record the outer namespace because we give ourselves the constraint that we want to do this operation repeatedly. So we need to undo the namespace jump. We need to jump back in the outer namespace. We record the identifier of the outer namespace. We don't need to care about what this identifier are. It's just an opaque value. So we do the setNS.set to jump into the inner namespace, and we make sure that we jump back using defer. Once that is done, we want to do our work. Seems easy. Unfortunately, it is not, because this code hidden a nasty surprise. I'm going to give you a spoiler. This nasty surprise is no longer true in Go 1.10, but how we get that is still interesting enough. We need to take a deviation to learn and to refresh some concept about the Go scheduler in order to really understand what's going on there. So the very bare minimum concept about the Go scheduler that make this issue present itself. Go code, the functions, run in goroutine. Goroutines are not operating system threads. They are lightweight threads, and those lightweight threads are multiplexed in system threads. So the Go runtime maintains a pool of system threads on which transparently run goroutines. This is why we pinned ourselves in the previous example. We pinned ourselves to a thread. Goroutines need, however, a context, a virtual process to be executed, and so threads need to acquire this context to run. And this is way deeper concept. There are much more to say, but for the sake of our story, it's enough. However, this is a link you can. There are links you can, like for example, I have one there. You can download the slides and see it yourself to learn more about the scheduler. So illustration about the concepts described in the previous slides. We have the AMS, which are operating system threads. The operating system threads have a virtual processor, it represents a virtual processor. It's not exactly like that, but close enough for us. We have the bluish dots, which is the active goroutine for each thread. And there is also a queue of goroutines waiting to be executed, grayish circles. If you want to learn more about the Go scheduler, it's a great topic. There is a link down there. Again, download the slides and you can have the links. So, key property of the Go scheduler, which is very important for our story. The Go scheduler can create new threads at runtime, meaning while our program runs. It does that to make sure that there is always an a free operating system thread, a free machine, M stands for machine, ready to execute our code. So our program always makes progress. But when the Go scheduler may create those new threads, for example, it creates them when we are just before entering a possibly blocking syscall, because the syscall so the kernel operation is possibly going to block. The Go scheduler creates a new thread. This new thread is created using the clone system call under Linux. We've seen that a few slides before. And this syscall allows us to create bots, processes, and threads. In the case of the Go scheduler, the flags we used in the clone syscall do not unshare namespaces. So the thread the Go scheduler transparently creates has the namespace on the thread we were running the code which could block. We will expand this in a moment. If you learn, there are again more resources about the Go scheduler, but these few words are enough to understand the issue. So let's try to visualize this concept about Go scheduler creating threads. We are on thread 1, we are happily running our Go routine. Our Go routine issues a system call which could block. So the Go scheduler kicks into play and creates a new thread which is available to run other Go routines, like in this example. After a while, our goroutine resumes execution because the system call unblocks, so it goes ahead. But the thread which we created, actually the Go scheduler created, it's available in the pool, so it could be used in the future to execute our goroutines, like in this diagram. What we expect to happen, what we want to happen in the scenario I described on which we jump in between namespaces is that the namespace switch, the green box I have there, it's only happening on the thread we locked our goroutine into. We don't want any other thread to change namespace because we want to have control about the namespace jump. So these slides represent what we expect, what we want to happen. Unfortunately, it is not what happens. What actually happens is what I have in this slide, on which the namespace switch happens. In the thread, we asked for it, but also in the thread that the Go scheduler creates for us, to make sure, for our own sake, to make sure that our program still has resources to run and make progress. But the namespace we jumped into somehow leaks and pollutes the global program state. So in the future, our goroutines may actually run in a random namespace, meaning we cannot actually control anymore on which namespace our goroutine is going to run. So it may or may not see the system resources we are looking for. And because of the Go scheduler works, we have no control about when this thread is going to be created, and surely we have no control about its namespace. We not explicitly control. But what about Lowcost Red? Does it help us? Yes, it does, but because it is not a fault. The goroutine on which you use the Lowcost Red is doing its job. The issue is what the Go scheduler does for us. In this case, we have to fight against it somehow. Again, the issue is in what the Go scheduler and the Go runtime created for us, not what we explicitly did, what it is implicitly done. So we will need some solutions. We will need some clever solutions, probably. There is a quick fix. If it is so hard, unexpectedly hard to switch namespace, let's just offload this task to a helper process. I mean, it's effective. So we want to run another simpler tool which does this job for us, because we cannot make it safely in our own main Go program. Unfortunately, this helper process is likely to be implemented in a different language, maybe C. Why that? Because if we do our helper in Go, we will face the very same issue we had in the main program, so little progress. So if we do that, it works, but we have a few issues. First and foremost, we have now our program in 2 different languages, may or may not be an issue. A more probably serious issue is that we have now a dependency. Our program is no longer self-contained, which is a nice property we get from Go, from the Go language for free. So again, this may or may not be a big issue, but it's not exactly a satisfactory solution. We have, however, a way out, because the very RunSea tool I presented before has exactly this issue, and this spoiler is how I learned of this issue in the first place. So how does RunSea solve this issue? Because it works. I mean, we run containers all day long, so obviously it works. It uses a package, a helper package, which is called AnnasEnter, which does safely this job, because it is actually but it is actually a C blob embedded in our own package. And so the helper tool I mentioned is actually embedded in our own program. Still, it's an interesting approach we want to explore. So let's zoom into the RunSea. RunSea is the core component of any Go runtime. In turn, the RunSea have a big chunk of logic in this lib container package, which is again from the coder.base. So it is battle tested. It proved itself. The thing is, lib container and RunSea are tied to each other. I mean, the design of lib container somehow leaks in RunSea. It's not something you drop in. You need to design carefully the interaction. Let's have a look at the Readme lib container. It's a good place to start learning about something. And we see that lib containers warns us that containers are run in a two-stage approach, which requires us to make sure that the program which uses lib container could be called with a new special parameter called init to act as init process of the container. Well, kinda like its inception. Maybe this is the way why everyone is using RunSea. Oh, this is just my hypothesis because it's complex enough to be re-implemented. So let's have a look, quickly look at the AnnasEnter flow, how AnnasEnter package does this magic. It hooks at the package import time. Back in time, when this package was incepted, the Go language did not allow goroutines to run at package import time. If not mistaken, this was changed around Go 1.0. But back in time, this is referenced in the early AnnasEnter documentation. This was not allowed. So we use this C helper to do the actual namespace dance. So we actually running C code inside our own Go program. The helper code has to fork twice to do this namespace switching dance. And this is an interesting concept because we learn actually the steps we need to do anyway in Go, because we can do that now in Go, but still the steps are important. And the steps are the same, both in C and in Go. And this package takes care of this synchronization between the child processes it creates, so we don't have to worry about them at all. So let's have a look at the flow from 10,000 meters above. We start importing this package. We need to import it when we need to run this namespace dance show. So we jump in the C blob immediately because the Go package is actually a thin shell around this C code. This C code tries to learn if there is work to do and does that reading by a pipe, which it reads the identifier and the file descriptor of this pipe through an environment variable. It's a bit messy, but long story short, this pipe is going to be filled by the program before the bit call again. Let's see that after a while because it is pretty complex. But if there is not work to do, the package does nothing. So we don't have unneeded processes floating around messing up our environment. But if there is work to do, we read what we learn, what we want to do from this pipe, and we fork to do that. We join the namespace using a multi-step approach, working around bugs of the Linux bugs once now fixed, or quirks about the implementation of the Linux package or of the Linux namespace, and we fork twice. Why we fork twice? Because most of the time we need to join the to change the PID namespace. There is no way to change PID namespace, so have a different view on the process tree without doing another fork, because otherwise the process identifier of ourselves, our own process, is going to change, and this is quite confusing. So the only way to safely change PID namespace is fork again, and this is the reason why we need two forks. We fork to create two helper processes. So in the second helper process, we do the final steps, like setting up user ID and group ID. And once that is done, we can complete, we call it a day, return to our caller, and keep going with our Go code. Because at this point we safely switch the namespace, and we have a handle we can use to run in the inner namespace we jumped into. Whoa, pretty messy. Not really, pretty complex. We have a simpler way out, just using Go 1.10 like I spoiled the fun a few slides before. Because in Go 1.10 we got a lot of fixes, but 3 are key for this very case, for this very story. And the most important fix is that the Go scheduler now promises us to do not create more threads while we are locked, while a goroutine is locked. So this alone makes our issue go away. So there are more fixes related to that, and related also to thread recycling, meaning threads that the Go scheduler creates and makes in the pool, which are available again later. So we can call it a day and just use Go 1.10 and be happy. Or not. Well, there is one situation we need to be aware of, even if we use Go 1.10, which is what happens if we run a goroutine after we switch the namespace. So this is the same snippet I presented to describe what is going to happen. If we run a goroutine ourselves, we have no guarantees about the thread, so the namespace, because the namespace is a thread property, this goroutine is going to run into. Of course, you can say, okay, this is trivial to spot, so, I mean, it is obviously going to be cached in code review. True, but you need also to check what the package you are using are doing. So it is not exactly that easy. The good news is that this check is relatively simple. So maybe in the future this is going to be automatically checked. Unfortunately, I'm not aware of any tool that could detect this kind of issue now. So we reached the end of this journey, and we can take some takeaways, which is, first, the unexpected hurdle is a smaller hurdle, but it is still a hurdle, so switching namespace, if you happen to need that, could be still worth extra attention. But the very evolution of this story tells us that Go is maturing fast, and all the complexity we had to deal with, for example, all the dance this AnnasEnter package did, so all the complexity the RunSea tool had to deal with is being simplified away by the evolution of the Go language. But still, the lessons which are encoded in these packages, are worth knowing. It's at least worth knowing. I believe that those issues existed and anyone solved them, because for example, the steps we need to solve the issue are still the same. So if we need, there is still quirks in the implementation of the Linux namespaces and many other things in the world. So it is those packages still have value, even though the Go language evolved meanwhile. This is what I have. So thank you, and I will happily take any question you may have. Any question?
So, in new versions after 1.10, if I call Lowcost Red, that means that only that goroutine will schedule on that host thread.
It means that the Go scheduler will not create threads. Will not create threads from that one, cloning that one. If you are locked and you happen to call possibly blocking syscall, you will not. Well, you will not get another thread created on your behalf while we are locked. So the namespace is not going to leak. To really properly answer you, we need to get into details of the how scheduler works. But I hope I gave you a good enough answer.
Okay.
Any more questions?
Okay, thank you again.
Thank you very much. Thank you very much.